Hello everybody, my name is Ole Mikkelsen and I am President and CEO of Sequoia Scientific. In October 2018, Sequoia co-organized the 6th Particles in Europe conference in Lisbon, Portugal. During 3 days of scientific sessions at PI, the question of how Schlieren could affect optical measurements came up several times. A paper I published with my co-authors in 2008 was brought up by the attendees to explain some of the data and results that were presented at the conference. The paper, The Influence of Schlieren on In-situ Optical Measurements Used for Particle Characterization, was based on data collected during my postdoc work in Canada and the UK between 2002 and 2007. It was published in Limnology and Oceanography Methods in 2008. In January 2007, I gave a presentation at University of Wales Bangor with most of the results in the paper. This is what you're going to see now, but read the paper anyway.
First, I'd like to acknowledge my co-authors, Tim Milligan from Bedford Institute of Oceanography, Paul Hill from Dalhousie University, Bob Chant from Rutgers University, Colin Jago, Sarah Jones, Vladimir Krivtsov, and Gay Metzelson-Jacob, all from University of Wales, Bangor. What is Schlieren? Have a look at this picture. What we are looking at here is a picture taken with an in-situ silhouette digital flock camera developed by Tim Milligan. The field of view is a 4 by 4 by 2.5 centimeter slab of water, so we are looking at a sampling volume of roughly 40 cubic centimeters of water. You can see a few black dots here and there. Those are the suspended particles that we are really interested in. But you can also see some squiggly lines covering most of the field of view. This is the optical manifestation of Schlieren, which is the mixing fog you encounter when two liquids of different densities mixes. This causes the index of refraction to vary, and thus the mixing itself suddenly becomes visible to us. If you are a diver and you have ever descended through a thermocline in a lake, you probably have seen this effect. Wherever we have density differences, we can have Schlieren effects, which can influence our optical measurements. If we can see the Schlieren with our eyes, then our optical instruments may also see them. The data in this paper were obtained in 2 locations with stratified waters, although the origin of the stratification is very different. The first location was in the Hudson River between New York and New Jersey in the USA. The sampling site was in a location where the Hudson is heavily influenced by tides and a salt wedge exists. The second location was in Cardigan Bay off of the west coast of Wales. This is a body of water that experiences seasonal stratification as the thermocline builds up during late spring and summer as the surface waters heats up. Here we see a number of plots and digital flock camera data from the Hudson River. The top left plot shows the temperature and salinity profiles. The temperature scale is on the top and temperature is plotted as the bold line. We see that the temperature varies from approximately 13.6 degrees Celsius in the surface to approximately 11.1 degrees Celsius at 9 meters below the surface. We also see that the salinity varies from approximately 4 in the surface to approximately 20 at 9 meters below the surface. It is obvious that we have a strong stratification, but how strong is it? In order to quantify stratification, there is a measure called the buoyancy frequency or the Brunt-Weisela frequency. It is computed from the gravitational acceleration, an average density, and the local vertical density gradient, delta rho over delta z. You can think of n as the angular frequency with which a tiny parcel of liquid will bounce up and down across the density interface. The higher the frequency, the more stratified the water. The buoyancy frequency is easily computed from standard CTD data. Some CTD software even output it as a computed parameter and then plot it as function of depth. This is what we have done in the top right plot. We can see that the buoyancy frequency increases to a maximum approximately 4.5 meters below the surface and then decreases again. On the right-hand side of the top right plot, you can see 12 dots, and 3 of them are marked A, B, and C. The dots mark the depths where we have in-situ pictures with a digital flock camera, so we have 12 pictures in total. B and C corresponds to the 3 flock camera pictures at the bottom. Note finally the 2 horizontal lines in the 2 top plots at approximately 3.8 and 6 meters below the surface. Images obtained between the 2 horizontal lines all showed varying degrees of Schlieren. This gives us a rough idea of the buoyancy frequency where we can expect to see Schlieren. Note that we are only showing one profile here, while multiple profiles were obtained. When looking at all the images where Schlieren occurred, we found that Schlieren-affected images did not occur at buoyancy frequencies less than 0.12 radians per second. Finally, note the circled area in picture A. This circle has the same diameter as the LIST 100 laser beam. We'll come back to this. Now, A few words about digital image analysis. When we want to analyze a picture, such as the ones from the digital flock camera for particle size, there's a few steps that must be followed. We must first define an area of interest we want to analyze. It is only very rarely that the entire image can be analyzed due to problems with lighting, vignetting, and other technical issues. In this study, an area of interest covering approximately 90% of the total image area was chosen. Then we selected a threshold value between 0 and 255 to discriminate pixels within particles from pixels in the background. There are a number of methods available to automate this in an objective manner, and we used Otsu's method published in 1979. Finally, one must apply some sort of connectivity criteria in order to define a particle. For example, a single pixel should never be counted as a particle. It could simply be a dead pixel in the camera. 9 coherent pixels were chosen as the minimum number of pixels to define a particle in an image. As the camera pixel size was 45 micrometers, this means that the diameter of the smallest resolvable particle with a digital flock camera was approximately 135 micrometers. Once the image had been analyzed, we counted all particles and computed various statistics such as area, volume, diameter, etc. During the processing, the area of interest was the same for all images, and as we shall see on the next slide, this means that the Schlieren pattern were included in the image analysis. We therefore analyzed all images a second time using a subjective approach where an area of interest was selected for each image so that it covered an area, however small, not affected by Schlieren. We denoted these two methods objective and subjective methods. Now we are starting to get some results. In the top left plot, we show the median particle diameter from the digital flock camera as a function of depth. The two horizontal lines are the same as before. All images obtained between the two lines showed Schlieren. The heavy line is the median particle diameter obtained using the objective method. The dotted line is obtained using the subjective method. We can see that the objective and subjective particle analysis fundamentally gives the same results above and below the region where Schlieren occurred. Within the Schlieren region, the objective image analysis method yields much larger median diameters than the subjective method. This is because the Schlieren pattern is analyzed as particles. We can avoid this using the subjective method where we deliberately choose an area of interest without any Schlieren patterns. The main conclusion from the top left plot is that the median particle diameter is almost constant throughout the water column. Looking at the plot to the right, we see the same pattern for the volume concentration. The two methods give the same results above and below the Schlieren region. Within the Schlieren region we have much higher concentrations. However, when looking at the subjective analysis, we see that in fact within the Schlieren region we do have a steady increase in concentration, which continues also below the Schlieren region. The main conclusion from the top right plot, therefore, is that the volume concentration is steadily increasing towards the bottom. The three pictures on the bottom are the ones we saw before. Note the square in image B. This is the size of the subjective area of interest. This area of interest was moved around on all images from within the Schlieren region in order to find the Schlieren-free section and then analyze that. We see that it is roughly 1/16 of the total image area, a lot smaller. This slide summarizes all of this. Fundamentally, we find that when analyzing Schlieren-free area of interests, we see no huge increases in median diameter or volume concentration in the Schlieren-affected images. We can conclude that in this case the median diameter was more or less constant and volume concentration generally increasing towards the bed. So what does the list see? Once again, we are looking at the data from the Hudson River. The three plots from left to right show the list median diameter, volume concentration and beam attenuation. The two horizontal lines again delineate the depths where the camera images showed Schlieren effects. From the plots we see that we occasionally have complete extinction of the laser beam. We have a beam attenuation and volume concentration of 0. We also see the same median diameter above and below the Schlieren region, and we see a generally larger volume concentration below the Schlieren region than above. More or less the same pattern we saw from the images, but without too much information about what is right and what is wrong within the Schlieren-affected region. We can also look at the volume scattering function from the list. Plots A and B in this figure shows the variation with depth of the shape of the volume scattering function as measured with the list 100 in profiles 2 and 3 in the Hudson River. The shape of the VSF above and below the pecnuc line, the red and the green lines respectively, appears similar. with the VSF below the pycnocline simply being displaced toward higher values corresponding to a larger particle concentration. The shape of the volume scattering function within the pycnocline is different though, with a hump developing around 1 degree. Plots C and D show the ratio of the volume scattering function in the pycnocline to the volume scattering function above and below the pycnocline. The ratio of the VSF below the pycnocline to the VSF above the pycnocline, the red line, is largely constant at all angles, indicating that the shape of the VSF above and below the pycnocline is generally the same. However, it appears that the shape of the VSF within the pycnocline differs from the VSF above and below by increased scattering intensity at angles below approximately 2 degrees, sometimes by more than 2 orders of magnitude. Let us now move to the second field location, Cardigan Bay, off of the coast of Wales, United Kingdom. On this plot we see the results of hourly CTD casts over a 25-hour anchor station, so 2 tidal cycles. The color scale, varying from 32.4 to 33.6, is the salinity variation. We see that we generally have a region of fresher water at the surface due to discharge from the Welsh rivers draining into Cardigan Bay and then advecting past the anchor station with the tides. This freshwater input from the rivers creates a halocline. The black line on the figure shows the depths of the maximum buoyancy frequency for each profile. We can see that the depth of the maximum buoyancy frequency varies between 5 and 10 meters below the surface throughout the anchor period. The buoyancy frequency values vary from 0.016 to 0.046 radians per second, roughly an order of magnitude lower than in the Hudson River, but very much in line with the buoyancy frequency typically found in the seasonal thermocline in European shelf seas. So what does the list see in terms of median diameter and volume concentration? The plot on the left shows the median diameter throughout the 2 tidal cycles, and on the right we have the volume concentration. The temporal variation in median diameter and volume concentration both show maxima in the pycnocline during the periods when the salinity difference is at a maximum. This slide shows the beam attenuation from each of the 25 profiles from the list 100, as well as from the transmissometer integrated with the CTD CTEC transmissometer. The 2 horizontal black lines and 5 and 10 meters depths show the variation in the depths of the pycnocline during the 25-hour anchor station. We see an occasional increase in beam attenuation from the list in the pycnocline, but there is no corresponding increase in beam attenuation from the CTEC transmissometer. The CTEC transmissometer did not record increased attenuation at the level of the pycnocline. This can be explained by the fact that the beam acceptance angle of the CTEC is larger, approximately 1 degree, than that of the list 100 type C, 0.05 degrees. This means that light scattered at angles between 0.05 degrees and 1 degrees will scatter outside the acceptance angle of the list, thereby increasing list beam attenuation, but inside the acceptance angle of the CTEC, leaving CTEC beam attenuation unaffected. This figure shows the volume scattering function from the list in Cardigan Bay. Plot A at the top left are all the volume scattering functions from the list measurements showing increased beam attenuation within the pycnocline. Plot B at the bottom left are all the volume scattering functions from the list measurements within the pycnocline that did not show increased beam attenuation. Plot C at the top right shows the average volume scattering function for the data shown in plots A and B. Plot D at the bottom right shows the ratio between the average volume scattering functions in plot C. From plot D, we see strongly increased scattering at angles smaller than approximately 0.3 to 0.4 degrees for the volume scattering functions associated with increased values of beam attenuation within the pycnocline. The increased scattering at these small angles would indeed cause an increase in beam attenuation from the list, but not the CTEC. To investigate the impact of the increased small angle scattering on the list volume concentration, all list measurements with increased beam attenuation in the pycnocline were removed and the temporal variability in the median diameter and volume concentration replotted after recomputing the 1 meter bin averages. We can see from the plot on the left that the median diameter maxima and its temporal variability in the pycnocline is largely unaffected by this removal, suggesting that it is real and not an optical artifact. However, the temporal variability and magnitude of the volume concentration maximum in the pycnocline is reduced. with volume concentration falling from approximately 150 cubic millimeters per liter to approximately 50 cubic millimeters per liter. Essentially the same values as for the volume concentration above and below the pycnocline. Apparently, no increase in particle volume occurred in the pycnocline. The overall observations are summarized on this slide. We note in particular that the list beam attenuation extinction can occur for buoyancy values larger than approximately 0.2 radians per second. Schlieren appears to be visible in images for buoyancy values larger than approximately 0.12 radians per second. Beam attenuation and laser diffraction measurements in regions where the buoyancy frequency is larger than approximately 0.02 radians per second could be affected by Schlieren. This means that Schlieren can potentially occur in the seasonal thermocline of shelf seas and lakes, and almost certainly in stratified estuaries and coastal regions affected by freshwater outflow, ROFIs, regions of freshwater influence.